All right, so I'm going to be talking about software integration challenges. My name is Todd Gamblin. I'm in the Advanced Technology Office at Livermore Computing. This is for the Collegeville Workshop, July 21 to 23, 2020. We build codes from hundreds of small complex pieces. If you go back to 2003, Tom Epperly and Paul Dubois had a paper where they said that this is an essential problem they don't know how to solve. Just when they're starting to solve the problem of how to divide codes up into reusable parts, it founders on the nuts and bolts problems outside the software itself. Component-based software development dates back to the 60s with McIlroy at the NATO Software Engineering Conference in 1968. He proposed this to the Navy because they had lots and lots of duplicative designs, and he wanted people to be able to rely on each other's software. The pros have been huge. Most modern software is designed in a component-based fashion. Teams can reuse each other's work. They have to write less code and meet deliverables faster, but they also have to ensure that the components work together. And so when you use components, you're really taking a lease on someone else's software, and you have to rely on them to ensure that it keeps working. The problem with that now is that integration burden increases with each additional library, and we have hundreds of libraries today. And so the management of all these dependencies is becoming unmanageable, and we want to automate more of the software integration process. If you look at exascale machines, this is the MFEM library. It's a finite element code from Livermore. It was relatively small before they decided that they were going to support the three different GPU architectures on the new exascale machines. And so to do that, they had to rework their whole memory model. They had to add 6 different backends. Whether they had to add 6 exactly is up in the air. They could have added a few, but they added a lot of backends, a lot of dependencies to manage the hardware, and they're still forced to make sure that their codes run on either the GPU or the CPU. And so this is a lot of work. So for performance portability, you're adding even more complexity to the software that people have to manage. Our code teams at Livermore, they embraced this modularity strategy in 2015 when they found that about 40% of most of our major multi-physics codes were duplicated, or at least served the same function. So they've been trying to consolidate on a core set of libraries and a core set of computational geometry features, mesh data, libraries, and so on. They still agree that this is the best strategy, but they have a challenge to get and pick up these codes. They have a hard time integrating all the different libraries because they all move separately, and they're the key here. You have to manage code from different people. There are other projects from Livermore, like Radius, that are trying to bring together all of our open source software. This includes a lot of the things from the modular strategic discussion on the previous slide. But basically, modularity is the way that people do things. And so there has to be a way to manage this stuff effectively. If you look at how teams integrate libraries, this is Mumi. It's a code that I guess it was featured at SC19. There was a Livermore paper on this code and the workflows that we built for drug modeling and cancer. And more recently, this has been used to model COVID-19. But it's a giant pipeline that includes a number of different codes for molecular dynamics, some AI, and some other things that are all orchestrated together. And the way that this is deployed is the developers, they determine some system library configurations that they want to use. They try to build the code. They fix bugs and configs based on errors that they get while they're building. And then finally, there's a productive period once they get the whole thing deployed. If there's an OS update, the application breaks and they have to go back and get things working again, or if they want to upgrade the library. And so this can be pretty complex. When they're determining system library configurations, it's about 100 lines with 20 different system dependencies configured per machine. And so they're pinning the MPI, they're pinning the OpenGL implementation, and so on. And they have a whole other slew of libraries after this that they fix. And the problem with this is that these things can change underneath them. And so even if the OS update comes along and changes things underneath them, that can break them. Or if they want to pick a new version of a library, that can break things too. So here's an example of a pretty harrowing dependency issue that they had. This is the Mumi code. Mumi is this piece up here. All of these other libraries, including things like Keras and Gromax is in here somewhere. These are things that constitute the Mumi code. They wanted a new version of Keras, and they thought that would be simple. And so the new version of Keras necessitated a new version of Theano, a new version of NumPy, a new version of OpenBLAS. The version they were using of OpenBLAS was the system version, which was too old. And so they had to build several versions before they found one that was ABI compatible with everything. And so if you zoom in on this, here's Mumi. Here's the subdag that they were dealing with in this mess of dependencies. It's OpenBLAS that had the incompatibility. They had to get this compatible with the system, and they had to ensure that it was compatible with GROMACS, with SciPy, and with FICE, which were the other libraries that were using OpenBLOS in their stack. And this took 36 hours to debug and to get a new version of OpenBLOS that was compatible. They had more problems with OS updates. So ABI compatibility with the PMI implementation on the system MPI on Summit was a huge problem. And that consumed hundreds of hours. And so they spend an awful lot of time dealing with things that are not really productive work. They're just deployment issues and library compatibility issues. If you look outside of HPC, dependencies are the most frequent source of build errors and software release delays. Google did a study of 26.6 million builds over 18,000 developers. And they found that dependencies were by far the largest percentage of build errors for both C++ and Java. ING had another study where they looked at what things contribute to delays in releases. And so they studied teams that were releasing rapidly and that were releasing slowly. And for both sorts of teams, other factors varied, but the #1 cause of release delays for both of them was dependencies and issues relating to them. And what this ends up doing is the developers avoid updates to avoid problems. And so they get security vulnerabilities. They don't get the latest performance updates, and the project stagnates, and it gets harder and harder to add new dependencies as time goes on. So projects that we're familiar with, like XSDK and E4S, have this problem too. XSDK actually pins a whole lot of versions for each configuration. And so they basically pick the thing that works. And they make sure that that continues to work. But what that does is, if you try to develop with this, it's incompatible with what it is that your software stack is doing. And so negotiating compatibility outside of this sort of circle of collaboration is hard. If you look at the software engineering at Google book from 2020, they outline 3 different ways, besides doing nothing, to deal with dependencies that have emerged in the past 10 or 20 years. And so there's this bundled distribution idea, the semantic versioning idea, and this live-it head idea. And so a bundled distribution is like E4S, XSDK. It's like your typical Linux distribution. You pick a bunch of versions that work together. Like I said, it's inflexible if you want to add a new version to this. So if you're doing development and you have packages that you control that are not really integrated in the curation of the OS, then you're out of luck. You need to use the versions there. And so you have to make your stuff work with it. Semantic versioning is what a lot of the user space package managers will do. So things like SPAC, NPM, Cargo, and Go. They use a convention called semantic versioning that's a rough proxy for compatibility, and they solve for a compatible set. That doesn't work very well because the versions are maintained by humans. And so at scale, your semantic versions are likely wrong, or they're overly constraining. And so you can have false negatives where you can't find a solution that works even though there is one. Or you can get builds that just don't work because people were too loose with their semantic versions and they said that they were compatible with things that they weren't compatible with. Google, Facebook, and Twitter, all the big companies, do something called live it head, where they try to keep their software, everyone works with the head version of the code. And they do something interesting to enable this. Every time you commit at Google, Facebook, or Twitter, your code is tested against everything that depends on it. And so you're on the hook for making sure that your dependents work. And so that's a lot of work for the developer. Not every team can really afford to do that. And this hasn't really been shown to scale outside of one organization, but it has been shown to allow these organizations to work effectively. So it has some of the same drawbacks as a bundled distribution. It puts the work in a different place. The developers have to make sure everything's compatible as they commit it. But it doesn't give you the flexibility of semantic versioning. You're still stuck with what everyone else is using. And so you need something that has all the pros and none of the cons of these approaches. What happens in the wild in our HPC ecosystem is that integration workflows, they fail because there's not enough compatibility information. If you have all of these different teams curating software distributions or making products and trying to integrate them into a community repository or into community projects, if you try to pick up something from each of these projects, then you're not going to be able to integrate it because they didn't curate it that way. And that's because you don't have information on how the libraries were built. You don't know, what's compatible, so you have to build repeatedly to find that. And you have hard constraints. So some developer said that they want exactly version X of some package. And that's probably overly constrained. They probably are compatible with some other version, but you wouldn't know because you can't examine the libraries and you just know what they told you. And so this holds up progress because people can't work together across different communities. And so we really want a way to work across different communities of developers. What I would propose people do is really get down into the meaning of what compatibility is. If you look at what current package managers do, they model things as a package name and a version. They typically don't model things like the runtime library. Most products just assume a version of a runtime library, and they assume that their consumers are going to use it. If you look at what really defines compatibility, it's the library, and then it's all the calls between them. So if you have package A, package B, and package C, A defines some functions, B defines some functions that A calls, C defines some functions that B calls, and the C++ runtime library is used by all of these, and it defines some functions that all the libraries call. Every function has some data types for its parameters, and that information is available at the binary level. It's in the dwarf info and in debug info. You can get it to some extent out of the binary without that, but it's very hard. And you do have the symbol names and symbols in all these different libraries. And so if you think about this, if you knew this stuff, you could make inferences about your stack that you can't right now. So if you upgraded version C here and you wanted to know what you needed to rebuild, if you redefine version C or if you make a new version of C and you have a new version of type T3, you really only have to rebuild B because B is the only one that sees T3. The rest of it remains compatible. If you change your C++ runtime, you'd have to rebuild everything. And this is frequently missed by package managers because they just don't care. They assume that it's common. So along with that, we need better package solvers that can actually solve using sound information. If you solve using versions like most systems do now, you're relying on humans to tell you what's compatible. They're using a very coarse approximation of compatibility. And you can produce a valid graph from that information, but it's not sound because it's not based in ground truth about what's actually going to be compatible. It would be really cool if we could generate entry and exit models of the ABI using binary analysis. So if you could actually solve on ground truth. And so with that, you could get rid of the human generated constraints and you could solve using these types of models, and you could basically, prove something, or you could build a linkable DAG by construction. You wouldn't have to do this search and you wouldn't have to rely on faulty information to do it. This is hard because it's a lot more stuff to solve than what current package managers do. It's actually an NP-hard problem, and you're adding a lot of information with this. But there's been a lot of improvements in solver technologies over the past 10 or 20 years, and so I think it's the right time to do this. So if we did this, it would enable way easier software reuse. If OS updates happened under a stack, you would know what changed by examining the ABI. You could identify what in the stack is no longer compatible, and you could actually rebuild a compatible configuration. If user requirements change and you need a new version, you could solve around that too, because you would know what's compatible. And you can actually tell the user if there's not something that would work. And then if information is not available, if we had this kind of insight into libraries, you could actually extrapolate from things you know and try to figure out a compatible configuration from that. So hopefully we'll be able to enable binary code reuse at some point, but right now we don't, and we distribute from source and people fight it a lot in HPC. Thanks.
Thank you, Todd. Great talk, and thank you for the gift of spec.
Sure.
I would like to ask about the optimization solver that you use.
Okay.
The problem I ran into in my professional life is that optimization solver produces results which are not that obvious to people who use it. And this is one of the reasons people try to stay away. Right, yes. Because it's not well understood. Did you see the same problem? How do you solve them?
So I've seen the problem that a lot of the SAT solvers that you can use will just return unsat. and so they will say, yeah, there's no solution to this. And it's, that's not too useful. There's ways you can get around that. There are solvers that will give you what's called an unsatisfiable core. And so if you monitor certain variables in your solve, it'll say like, these are the things that are incompatible. And so that's pretty useful. And there's also tools like, so I don't know if you've heard of Z3, it's what a lot of compilers use for doing these kinds of SMT solves, but it'll spit out a proof of why something is unsatisfiable. And you can actually take that and construct useful error messages out of it. There's a project called PubGrub for the Dart package manager that actually does this, where in the CDCL solve, they will record what the conflicts were, and they'll give you a chain of conflicts that resulted in the unsatisfiable graph, so they can give you more information. So I think you really need something like that. I don't think most of the industrial solvers are geared towards that. So yeah, I think a lot of work needs to be done on the solvers before they're really suitable for really telling people what's wrong with their package stacks, but I think it's doable.
All right, thank you so much. Thanks again.